In this section, and actually the next couple of sections, we're going to be looking at finding volumes of solids of revolution. And so what that means is we are going to take a curve, so you can kind of look at maybe this first graph down here, and we're going to revolve it around an axis, and that's going to end up giving us a volume of a three-dimensional region that we want to find. So before we even get into anything, let's just kind of take a look at some visualizations here. Now, some of you may have seen these decorations. This is a really good example of the revolving of a curve. Here's another, okay, so here's a basic graph. So suppose I took, you can see this person, it's like a crafts website, but it's a really good illustration for initially just thinking about a volume of revolution. So they're like making this heart-shaped decoration. And if we could take that curve that they're holding there in that second picture and place that along the x-axis or the y-axis and come up with an equation of that red curve, and then we open that up into that decoration, kind of like you see here, that is a really good mental visual of what we're doing with a volume of revolution. We start with a curve, we revolve it, and we get this three-dimensional region. Okay, so that's the first thing that we want to be thinking about. Now, how are we going to find this volume? In this first video, we're going to introduce this disk method. Okay, so again, lots of great visuals out there. And the first one I want us to take a look at here is, this is a really short video, and let's take a look at this.
Here is an illustration of our cross-sections idea. Let's take this apple here, and in order to approximate the volume of the apple, what we'll do is we'll slice it into all these little pieces, and we can find the radius of each individual slice, right? And if we were to add all of those up, that would be the idea of our cross sections, and the more slices that we create, the better approximation to our actual that we get.
So that gives you in like a really, really quick sound bite. And it's kind of a fun thing to do if you're in class with students. Give them cutlery, give them knives, I say, and let them cut up some fruit, whatever your favorite fruit is. And it's just this intuition that a lot of times emerges from students, like, how would I find this volume? Well, I might cut it into things that resemble discs and kind of approximate these volumes. So here's what we're doing. So kind of one last little illustration before we get into the nuts and bolts of this here. And this is, now we're getting real mathy, right? So we went from, holiday decorations into apples, and now we're real mathy. We're in GeoGebra here. All right, so as we take a look at, and I'll definitely, this is one I will post on our website. This is a great one. You can enter a function. And you can see in the left side here, there's the area. And then if you revolve those rectangles on the right, and if you kind of click on it, you'll be able to move it around and sort of see that three-dimensional region that's being approximated by these discs. And then what happens is if we increase the number of discs, you can see the rectangles increasing up there on the left. And then you see as we get a better approximation, our volume is becoming more precise as well. We're getting a better approximation for the volume. So this is a great one that you can look at on your own as well, and I will definitely post that so you'll be able to see that. So let's get into it. So hopefully you have a pretty good mental picture. So what we're going to do is we're going to take a curve. We are going to take a representative rectangle that you can see here of radius r. So that radius r is typically often going to be a function of x. So, because depending on where you would draw your radius, obviously your representative rectangle, I could have drawn my representative rectangle over here, and then that now has, of course, a different radius, right? So now my radius is going to look a little different, because it's going to be defined by the height of that curve. So this is the radius of the disk that we are revolving. So that's why this r, this radius, is often going to be defined by the function r of x, I'll call it, like an f of x function, but I'll call it r for radius. We revolve that rectangle, we get a representative disk of width delta x, and then we can approximate the volume by those n disks. All right, so what's the volume of a disk like that? Okay, well, if we think about take one of these big discs and, think about kind of laying it on its side, if you will, kind of think of it maybe more kind of as it's on its side. And then it might become a little bit more clear. It's going to be the area of your base, which is going to be pi times whatever that radius is. So pi times your radius squared, and then times what would normally be what we would refer to as the height of that disk. Now, that's turned sideways. Now, if you flip that back up, and let's say that this is representing, one of those disks. I've turned it on its side for us to think about it first. But now, okay, well, what's that going to be? The radius of that representative disk is going to be whatever that r of x is. That will represent my radius, and it will change, along all of these little representative rectangles. So that's why it's this r of x. And the height, this is going to seem a little weird. What happens when I turn this on its side? This is what was the height, and that is now that delta x. It's actually the width of the partition. So it may seem a little strange to say the height is delta x, because mentally you may be thinking to yourself, well, wait a second, isn't that height really equal to, isn't delta x a width? And yeah, it kind of is, but that width is really going to represent the height of our disk here. So that would be the volume of one disk. So here's going to be a common theme that we are going to see that we developed with the area back in Calc 1. So we get an approximation for the volume. That's what the little Apple video was talking about as well. We're going to take the sum as I would go from 1 to n of r of x sub I, because obviously all those radius measurements will be different along that, interval from A to B, let's say. And then times r, we'll just stick with a common width. There'd be no reason to not, so just delta x there. And so that would be an approximation for the volume. And then what do? Well, we say, let's find the actual volume by letting the number of rectangles, taking the limit as n goes to infinity, of that Riemann sum. And so this is how we develop a lot of our applications, kind of look at one slice, one partition, sum n of those, and then look at what happens when the limit as n goes to infinity, and what we get is our definite integral. So that is what we have right on the top of this next page here summarized. So what we see, and here we're starting with a horizontal axis of revolution. So I want you to kind of always be thinking about pi r squared. That's like the area of a cross section when it's rotated. It's that circle area, and then times the delta x is going to become the dx. That is the width. And so what we end up with looks like on the definite integral from a to b, we are going to have pi and then that radius squared dx. Now, you can do a couple of things here. Pi's constant multiple. If you so prefer, you can bring the pi out in front. So pi times the definite integral from a to b of this r of x quantity squared dx. And the important thing to note here is that, and I'll even sort of write that next to the curve here, this r of x, this radius, this is typically just like some given function of x. So I'll just say, this is often, the function that is given to you. It's often just an f of x. I'm calling it r of x to really kind of drive home the notion of the radius here.